Once again, good morning to one and all. Myself, Arun Kumar K, Assistant Professor, Aeronautical Department from MLR Institute of Technology, Hyderabad. So, in the previous lecture, we discussed about basics of second law of thermodynamics. So, in that, we have discussed about Clausius statement, Kelvin Planck statement, and entropy statement also we discussed. In today's lecture, we are going to discuss about this application of second law of thermodynamics with respect to the various engineering components. So, in that actually, generally we are going to consider one as heat engine and other thing is nothing but we can able to say heat pump or refrigerator. Only a slight difference we are having with respect to the heat pump or refrigerator. Right. So, we'll discuss about the heat engine. See, we'll start with the heat engine first. So, the heat engine is nothing but, see, we are having general case two reservoirs we are having. One is nothing but source, which is having a high temperature, and another one is nothing but sink. That is what actually we are having as low temperature. This basics and all we discussed already in the Clausius statement as well as Kelvin Planck statement. So, with that basics actually, hereafter we are going to consider the system with respect to the source and sink. Right. So, we have to assume that heat engine is working between this source and sink. So, everyone knows that the purpose of heat engine is nothing but to produce a useful mechanical work done. Right. It absorbs heat energy from the source and produces mechanical work output, and some amount of energy is transferred to the sink. Right. That is because of the low temperature we are having. Right. See, the heat engine is a system that converts heat or thermal energy to mechanical energy. Right. So, I said useful mechanical work done, I said, right. So, that is the conversion we are having, which can then be used to do mechanical work. So, the purpose of generating that mechanical energy is to do some work, right. So, that is the basic purpose of the heat engine. So, we can able to consider our two-wheelers and four-wheeler car engines also we can able to consider, right. From the source is nothing but actually we are getting from the calorific value of the fuel. That sink is nothing but obviously with respect to the some cooling system, or we can say the atmosphere also we can able to consider as a sink, right. See, do mechanical by bringing a working substance from a higher state temperature to a lower state temperature. This higher state temperature is nothing but actually we call it as source, and this lower state temperature is nothing but actually we call it as sink. So, these are the two thermal reservoirs actually we are having. So, for simplification and for simple understanding purpose actually we have considered this as reservoirs, right. So, these are the source and sink actually we are having. In between this, this heat engine is operating, right. See, the working substance generates work in the working body of the engine while transferring heat to the colder sink, right, to the lower temperature until it reaches a low temperature state, right, until it equates the equilibrium conditions with respect to that colder sink and the temperature, right, until it transfers the heat to the colder sink by converting some amount of energy to the mechanical work done. So, that is what this heat engine works, right. So, inside that heat engine we are having many systems. So, the main purpose is to generate the mechanical work done. So, how it is generating? By transferring some amount of energy to the sink also. It will happen according to the second law of thermodynamics. Now, actually we can able to include the losses to this particular engines or machines, right. So, now actually I can able to calculate the performance of the particular engines or thermodynamic component, right. So, that is the application of second law of thermodynamics actually we are having. See, during this process some heat is normally lost to the surroundings. Is that right? So, that is what that I have said actually the cooling system or surrounding atmosphere is nothing but a sink actually we supposed to consider. So, because of that actually some amount of heat compulsorily we will lose actually to the surrounding and is not converted to work. So, which means if it is not converting into work, then this heat conversion is nothing but actually heat transfer is nothing but we supposed to consider as losses, right? Also some is unstable because of friction and drag. So these are the actual cases actually we supposed to consider. So these conditions actually we didn't discuss in the first law of thermodynamics. So after this Clausius and Kelvin Planck statement, we are discussing with respect to this losses also, right? So in this way actually we can able to understand the application of second law of thermodynamics to the thermodynamic components. So that is what the heat engine actually we have considered, right? It obeys the Kelvin Planck statement, right? See, listen here. This is nothing but the heat engine I'm having. Inside that actually various systems we are having, right? So that system consumes energy from the hot source. So that is what the high temperature we are having. How we are getting that actually from the calorific value of the fuel, the thermal energy is generated. Because of that high thermal energy, it is maintaining at the high temperature, right? And because of some surrounding and some cooling system or agents, whatever actually, some amount of heat is transferred to the sink, right? And only some amount is converted into mechanical work done. So this is the working principle of heat engine actually, right? So based upon the second law of thermodynamics, especially based upon Kelvin Planck statement, we can able to say, right? Yes. So the next one is nothing but actually, say if I calculated, if I assumed in this way, then I can able to easily calculate the efficiency parameter also, right? See, that is what the performance parameter. See, in the first unit, we didn't discuss, we can't able to discuss because various serious limitations actually we are having the first law of thermodynamics. Once we're done with the basics of second law of thermodynamics, then I can able to calculate the efficiency parameter also. This is what the performance parameter, right? So the performance parameter is nothing but actually usually we need to mention in terms of neta for the heat engine, right? So we know that what is the heat engine is nothing but always output by input. What is your output actually? The mechanical work done is nothing but my output. What is your input? The heat supplied is nothing but input. That is what they have mentioned as QH, right? Q denotes heat and H denotes hot reservoir, which is maintained at a higher temperature state, right? So from this actually we can able to calculate. See, listen here. This is our, what is the W actually we are having? W is nothing but we are having as we got the input from QH. Some amount is QH is converted into two parts, right? One is nothing but W and other one is nothing but we call it as QC. So W plus QC is nothing but is equal to QH. Is it right? So the W is nothing but actually I can able to write as QH minus QC. So this is what actually we have got W equal to QH minus QC by QH. So this equation actually I can able to write in the simple form. That is what 1 minus QC by QH, right? QC is nothing but actually some amount only energy only transferred to the sink. That is at the lower temperature. Say instead of amount of energy, I can able to say with respect to the temperature TL by TH, right? So obviously this is nothing but we are having always less than 1, right? So always less than 1 in the sense neta has to be always less than 1. We will get 1 minus of this answer will be always less than 1, right? We won't get in terms of negative actually, right? So this is what this heat engine states with respect to the Kelvin Planck statement. Right? So now straight away we'll move to the pump, right? So heat pump or refrigerator racer. So first we'll discuss with respect to the heat pump. Only the few differences actually with respect to the objective. We are having the difference between this heat pump and refrigerator. Apart from that, both the concepts are same. Both the working principle are same, right? See, the greater advantage of using a heat pump to keep your home warm rather than just burning fuel is that a heat pump supplies. See, this is what the heat pump supplies to the room. See, in order to understand the heat pump, we have to assume the good example as just assume during the winter season, right? So we supposed to turn on the room heater. So in the surrounding actually I'm having around say for example we are having as 15 degrees Celsius. Right? During the winter season, so average surrounding temperature we can assume as 15 degrees Celsius. Whereas in the room temperature, if you are keeping that as 15 degrees Celsius, right, it is very hard to handle that. So we need to increase, we need to warm, right, your home. So for that, you supposed to turn on the room heater. So what is happening actually? It is transferring heat from the sink to the source, right? So based upon the Classier statement, we know that we can able to transfer the energy from lower body to, that is what, colder body to hotter body. That is what the Classier statement states until if you apply the work input to the system, right? So in order to keep the room or home warm, right, I supposed to absorb energy from the atmosphere, but it is already low. So for that, I supposed to need to do more works. So that is where the work input I supposed to supply, right? So here the surrounding is nothing but the source temperature, and the room is nothing but your sink, right? So that is why I said in order to understand this heat pump, we supposed to assume the room heater or air conditioner also we can able to assume, right? Okay, no? So in that way we can able to assume. See, the heat transfer is from outside air even at a temperature below freezing, right? Even the temperature is below freezing also we can able to consider, like even 0 degrees Celsius, even minus degrees Celsius also we can able to consider to the indoor space, right? Indoor space is nothing but the room or the home which we consider, right? So this also it is possible, right, in the actual cases, but in the first law we didn't discuss about this thing. So after applying this basics of sign law of thermodynamics, we can able to understand that we can able to transfer the heat from cold body to hot body also, right? So in order to do this, you only pay for work, right? Until some expenditure, right, I can't able to do this transfer, energy transfer. So for that actually I need to pay for W, right, and you get an additional heat transfer of QC from the outside at no cost. Because of the sink actually, obviously the heat transfer will takes place, right? That is a sign of thermodynamics we are having. So the QC from the outside at no cost it will takes place. That is what the we can able to consider as losses in many cases, right? At least twice as much energy is transferred to the heater space as is used to run the heat pump, right? Okay, na? So which means more energy we supposed to use it, right? More actually we supposed to pay for that, right? So that is what the statement given. So this is what actually we call it as the basic principle behind this heat pump, right? See, I can able to transfer. Listen here. This is what the TC. Assume this TC is nothing but the outside outdoor temperature. That is what the surrounding temperature during winter season. Assume there is a 0 degrees Celsius like that, right? The room temperature I need to maintain around 20 degrees Celsius. Got it? So which means I supposed to do some work input to the system and QC also transfer to the system. What happened actually? These two things traveling towards this, and the summation is nothing but we got as QH, right? We got as QH with respect to that. So this is what the work done against friction is lost to cold reservoir, right? So which means whatever the ideal condition work done actually we have assumed, right? But apart from that, I supposed to do more work if I include this loss, friction losses also. That is what it states, right? So this is about actually we are having as heat pump, the schematic diagram. See, for the heat pump, the quality of the heat pump, quality is nothing but again the performance parameter, right? The quality of the heat pump actually we can able to judge by how much heat transfer QH occurs into the warm space compared with how much work input is required. So the desired output by the input, right? Which is your desired output actually? I need to maintain the room temperature, right? I need to increase the room temperature. What is that room temperature actually I'm having? High temperature. So that is your source actually over there. That is your source over there. Atmosphere is nothing but your sink, right? So that is my desired work actually. Got it? So because of that actually we can able to say that the performance parameter as coefficient of performance, right? So what is that actually? What is your output actually? Output is nothing but I need to transfer the heat to the source. Which is the source? To the room, right? So in this terminology actually we have considered as whatever the heat transfer happening with respect to the source, that is what the QH. That is your desired output by W. By W. So in this way actually we supposed to calculate the coefficient of performance. See, you can put up the question like in earlier case for the heat engine, the neta is nothing but actually I have said as output by input, right? But here actually we are telling us one more parameter is nothing but COP, coefficient of performance. Why? Because for this performance calculation, say for example instead of COP, if you consider this as neta also, we'll get more than one actually, right? So we'll get more than one. We know that the efficiency of the particular engine is nothing but always for the ideal cases actually we have assumed in such a way that it is 100%. 100% is nothing but 1 unit, right? So it is always less than 1 actually. So that is why we term it as different terminology. That is what coefficient of performance instead of neta. Why? Because we are going to get greater than 1 for this calculations, right? So that is why actually we can able to say this as COP instead of efficiency, right? See, for example, I am telling you the work done required for the ideal condition, right? To transfer the heat from outdoor to indoor. For the ideal condition, if it is 100 kilowatt, if I required. In the actual cases, actually, I supposed to required 150 kilowatt because of the losses, friction losses. That is what we discussed, right? If I assume this as then neta over here, right? The ideal case condition is nothing but greater, but the actual case is lesser actually. So that is why we are term it as COP, right? So that is the difference between neta and COP we are having, right? Yes. Since the efficiency of any heat engine is less than 1, see, it means that the COP is always greater than 1. So that is why instead of efficiency we are term it as a COP, and a heat pump always has more heat transfer QH than the work input to it, right? Why? Because the combination of QC plus W equal to, we call it as QH, right? So that is what it terms, right? See, the next one is nothing but actually refrigerators. See, I said a heat pump or a refrigerator. I didn't mention heat pump and refrigerator. So both the functions are same actually, right? Both the functions are same, but which is the desired effect actually we require. See, for the refrigerator, we supposed to consider the refrigeration which we are having at our day-to-day life, right? At home we are having. That refrigerator is nothing but actually we are having that as cool temperature. We need to freeze the temperature. We need to reduce the temperature. What is the atmosphere temperature actually we are having? That is always higher, right? So here the atmosphere is nothing but source, and the space to be freeze is nothing but we call it as sink, right? So with the example, heat pump actually from outdoor to indoor we transfer, but whereas here indoor to outdoor we supposed to transfer, right? So let me show you with a schematic diagram first of all. Before that, see, refrigerators are designed to cool something down in a warm environment, right? So the warm environment in the sense summer season actually we supposed to assume the summer season average temperature of atmosphere is nothing but around 30 degrees Celsius in India, like that we can able to assume. But whereas I supposed to reduce the temperature to 20 degrees Celsius in the room, right? So which means I need to extract energy from the room and I supposed to transfer to the surrounding. Got it? So here this is nothing but actually room temperature or we can say the space required, right, to cool something down, right? That is what actually we call it as a sink, right? So both works under the same principle. We are transferring the heat from sink to source only, right? But the atmosphere we are considering in the previous case as sink in the heat pump, but whereas in the refrigerator we are considering the atmosphere or surrounding as the source. That is the difference between this heat pump or refrigerator we are having, right? See, the quality of air conditioners, right? AC also we can able to take this as an example. Refrigerator is judged by how much heat transfer. See, earlier actually we discussed with respect to QH, but over here it is QC. That is what I said, desired effect, right? Occurs from a cold environment compared with how much work input W is required. That is with respect to the expenditure of work, right? That is same actually. But the desired effect is nothing but how much heat transfer QC occurs. Whereas in the heat pump we discussed as QH occurs, right? So that is the difference actually we are having. That's it. See, what is considered the benefit in a heat pump is considered waste heat in the refrigerator, right? So that's the vice versa manner we supposed to consider. Yes. See here, this is what actually the TC. See, for TC and for refrigerant heat pump, we are having the same diagram. But whereas in the heat pump actually, the TH I assumed as room temperature, right? The space provided, right? But whereas here actually, the TC is nothing but the room, right? Or the space provided, and TH is nothing but the atmosphere, surrounding, right? Whereas in the heat pump, it got reversed actually. But other processes are same actually, right? It depends upon, that is why I said desired effect. So for refrigerator, you just assume, or air conditioner, you just assume the summer season, and the room heater or heat pump, you have to assume with respect to the winter season, right? So with that actually we can able to understand the working principle of refrigerator also, right? So inside that actually various systems we are having. So this is what the refrigerator or heat pump combinedly we have shown. So that is what already we discussed actually. From cold environment to warm environment, it is taking place, right? But the required desired effect actually we supposed to consider with respect to the refrigerator or heat pump. Yes. See how to calculate COP for this. Earlier I said the COP for the heat pump, that is what QH transferred occurs by expenditure of work input. But whereas here QC by work input, right? See, noting again that QH is equal to QC plus W. The cases will be same actually, right? The cases will be same, and we can see that an air conditioner will have a lower coefficient of performance than a heat pump, right? Why? Because the QC actually I have considered, the QH is nothing but the greater always for the both the cases. So that is why it is having a lower coefficient of performance than the heat pump, right? But it is also having greater than 1 only, COP also. That is why you are mentioning, not mentioning in terms of data, right? So heat pump is nothing but QH by W. What is QH actually? For the both the cases, QH is always greater than QC plus W. Whereas QC is nothing but, if I consider QC, what is that QC? QH minus W. So some parameter is reducing actually, right? So that is why they have mentioned as lower coefficient of performance, right? But both will be greater than 1 only, right? So this is what about actually heat pump, refrigerator, or heat and heat engine, right? So this is actually we have applied the Kelvin Planck statement for the heat engine and the Classe statement to the refrigerator or heat pump, right? So this is about actually the application of sign law of thermodynamics to the thermodynamic component, right? So thank you everyone. We'll see in the next lecture. Thank you.